So, good evening everyone. So, welcome to my YouTube channel, Avatarm. So, today we are going to see fifth lecture on uniform convergence of functions. So, in this lecture, we will study a method to check a uniform convergence. Maybe someone can find it easier than previous one. Okay. So, let's start. So, to study that method, we need a result. So, we start with the following theorem. Let Fn be sequence of functions okay such that Fn converge and Fnx converging to F pointwise. It means F is pointwise limit of F. What does it mean? It means Fnx limit n tending to infinity. Fnx is equal to Fx for each x belongs to I. Then Fn converging to F uniformly if and only if this is uniformly. Okay. So let's write it. Maybe some is telling. So Fn converging to F uniformly. If and only if Mn is equal to supremum of x over I Fn x minus Fx. This tends to 0 as n tending to infinity. Okay. So let's see its proof. Okay. So first suppose that or assume that Fn converging to F uniformly. Okay. Then what does it mean? So given any epsilon greater than 0, there exists. So this converges uniformly on I. Okay. So given any epsilon greater than 0, there exists a natural number capital N belongs to natural number set such that Fn x minus Fx is less than epsilon for all n greater than equal to capital N, x belongs to I. Okay. Okay. So now, now we can go then if I am if now fix n belongs to n and n is greater than equal to n, we have what we have. So we have Mn is equal to supremum x belongs to I Fn x minus Fx. You see that if this quantity is less than epsilon, So supremum will be less than equal to epsilon. Okay. So this implies Mn is less than epsilon for all n greater than equal to n. So what does it mean? If I will take limit, so if I will take limit, because this is a non-negative quantity, so this implies limit and tending to infinity, Mn will be less than epsilon. Okay. But epsilon is greater than 0 and epsilon is arbitrary. So we get, what we get? We can make epsilon as small than s. Okay. So what does it mean? We can take epsilon is equal to 1 upon m or 1 upon n and tending to infinity. It will be 0. So I can take epsilon as small as. So what does it mean? It means that this is nothing but limit because we have a note that if a is greater than 0 and a is less than equal to epsilon for any epsilon greater than 0, then a has to be 0. Same technique. So what we have, because this is 0 and lower bound is 0, upper bound is also 0. What does it mean? It means limit has to be 0. It means this limit is 0. So it means Mn tends to 0 as n tending to infinity. Okay. Now take reverse direction. Conversely, assume that Mn tends to 0 as n tending to infinity. It means Mn is equal to supremum x belongs to I fn x minus fx tends to 0 as n tending to infinity. Now Mn tends to 0. What does it mean? Mn tends to 0 means what? Given, this implies given any epsilon greater than 0, there exists n belongs to n such that Mn, because Mn is non-negative, so Mn is less than epsilon, okay, for all n greater than equal to n. So what does it mean? It means supremum x belongs to I fn x minus fx is less than epsilon for all n greater than equal to capital N. But we know that supremum is always greater than these values. So fn x minus fx is less than supremum x over I fn x minus fx less than epsilon for all n greater than equal to capital N and x belongs to I. So fn x minus fx less than epsilon for all n greater than equal to n and x belongs. So what does it mean? What is the meaning of this statement? The meaning of this is Fn converging to F uniform. Okay. So we have proved this. statement. Now, okay, so we have done this theorem. Now we have to note one thing. Suppose I have a smooth function. Suppose f is a differentiable function. On R. Okay. Okay. Now, and f is non-negative. It is non-negative and it is not a zero function. Okay. If limit n tending to infinity plus minus infinity fx is zero. Okay. Then what can you say? Then supremum of fx is achieved at some maximum value, at some maximum points, at some maximum points of fx. People mainly use this concept here. Okay. So see this question I am telling you. So what is first question? You see this question. So let fnx is equal to nx upon 1 plus n square x square. So this is x. Okay. Nx. So does fn converts to zero function? So is fn this sequence converges, or it does? I should write does it. Does fnx converges uniformly on R? Okay. So let's see its solution. Now first see its quantized limit. So what is quantized limit? We have already solved such examples also. So if x is 0, then what can you say? Fn 0 is 0. But I can put here 1 plus n square into 0, that is 0. So this will be tends to 0. So f0 is my 0. Because pointwise limit f will become, and so f at 0 is 0. Okay. Now if x is not 0, so limit and tending to infinity fn x. What will be this? Limit and tending to infinity nx upon 1 plus n square x square. You see that this will be infinity and the numerator is infinity, maybe plus infinity minus infinity, it does not matter, but it is infinity. And numerator denominator is also infinity. We can use, so it is indeterminate form because it will make infinity but infinity indeterminate form. Next form. So we can use L'Hospital rule. Okay, so you use that rule. So n tending to, so x upon 2n x square. So 1x will be cancelled out. So now this is limit n tending to infinity. So 1 upon 2nx. So 1 upon 2nx. So x is non-zero. So this is 1 upon infinity, that is, or maybe plus minus infinity, depending on x is positive or negative. So ultimately this is going to be 0. Okay. So what is f? So if x is not equal to 0, we have x is equal to 0. So what is your pointwise limit? This is actually 0 function. So f is your 0 function. Pointwise limit is 0 function. So f is 0 function. 0 function. Okay. Now, so we got pointwise limit. Okay. So what is about mn? Mn is equal to supremum of x belongs to I, f and x, but f is 0, so it is nothing but x belongs to R, I is R. So nx upon, okay, so we got this one. Now, what will be the maximum of this function? So we have to find maximum of this function, then it will be maximum. Okay. So I am taking let nx is equal to y you take. Okay. So here n is fixed. So here n is fixed. So n is fixed here. I am taking a fixed n. N is fixed. So and I am considering this function gx is equal to nx upon 1 plus n square x square. So we have to achieve what is the maximum value here, because limit is tending to 0, we know. So what is? So dfn upon dx. What is this? What is this? So what is this? 1 plus n square x square का square 1 plus n square x square. So differentiation of it, n minus nx, differentiation of is 2x n square. So you can multiply inside n cube x square minus 2n cube x square upon 1 plus n square x square square. So what is this? N plus n minus n cube x square 1 plus n square x square. So maximum point where exists. So for that we have to keep it 0. So n you can take common, n 1 minus n square x square 0. It means n is non-zero natural number. So n square x square 0. So n is both x square you will get plus minus 1 upon n. Okay. So what will be the supremum? So Mn is equal to, we have to find supremum. X belongs to R. Fn what is that? So N, so what is that? Supremum. Supremum will attain at this point. So put that point. Plus minus 1 upon N. 1 plus N square plus minus 1 upon N square. What is this? This is 1 and this will be cancelled out. 1 plus 1, that is 2. Sorry, 1 upon 2. So Mn, what you got? Mn is actually 1 by 2 for all N belongs to N. So what does it mean? It means that this sequence do not tends to 0. So Mn, because this is fixed value and that does not tends to 0. So this implies Fn does not converge uniformly on R. Okay. Now see second example. Question number 2. Does Fn x is equal to x upon 1 plus n x square converges uniformly? This is x, this is n. And converge uniformly on R. So you can also check it. Fn x is equal to x 1 plus n x square. We can change this function to earlier form. Earlier question, how we can change it? Because I can write this function as under root n x square. So I can multiply with under root n and divide by under root n. So my this function inside thing is little bit similar to that one. Only n is replaced by under root n. Does not matter. So it will be, its limit will Fn will converge to 0 function pointwise. You can check it. Okay, pointwise. And what will the Mn here? You can check Mn will be, so it will be come out supremum of under root n x upon 1 plus under root n x square. And its supremum will be attained at plus minus under root n. So this will be 1 upon under root n, 1 upon under root n, plus minus and x value will become under root n. Okay. So this is, what is this? And what about this? So this is mod. So this will be, after solving it, you will get 1 in numerator, and denominator you will get plus minus 1 square. So that is 1 upon 2 under root n. Okay. So Mn is 1 upon 2 under root n for all n belongs to n. But this tends to 0. But when n tending to infinity, it tends to 0. So what does it mean? It means that Fn converges to f, Fn converges to 0 function uniformly on R. Okay. Now we see another example, question number 3. Because Fn x is equal to nx upon e to the power minus nx square x greater than equal to 0 converges uniformly on closed interval 0 infinity or not. Solution. So Fn x is equal to nx e to the power minus nx square. Okay. So what is limit n tending to infinity? Fn x is equal to for 6x. For 6x belongs to 0 to infinity. What is we have? We have limit. What is this limit? Limit n tending to infinity nx upon. We can take this in denominator. And this is indeterminate form. If we are taking 0, this is 0. So this limit n tending to infinity, Fn 0 is 0. Because x is 0, na? So this is 0, so this will be 0. It means F0 is 0. And if x is not equal to 0, then what will happen? If x is not equal to 0, then F0 is limit n tending to infinity Fn x, that is limit nx upon e nx square. So it is making indeterminate form, infinity but infinity. So we will differentiate, okay, in numerator and denominator. So this will be x upon e nx square into x square. So x will be cancelled out. Limit 1 upon x e n x square. So in denominator it will be infinity and it is going to be 0. So this is, so what is f function? F function is nothing but 0 function. Now we have to calculate its for 6n. We have to calculate Fn x. Fn x is nx upon e nx square. We have to, what is the supremum? So max point will be calculated. We have to find. So dfn upon dx is equal to n e minus nx square nx, okay, e nx square minus 2nx, okay. So it will be, so take this common. It will be 1 minus 2n square x square. Put this 0. This part is non, this is positive quantity. So what you will get? 1 minus 2n square x square is equal to 0. So what you will get? X is equal to plus minus 1 upon under root 2 into n. So got this. So what is Mn? Mn is supremum x belongs to 0 to infinity nx minus nx square. So put these values here because f function is 0. However, negative value cannot take. Okay. So this is n upon under root 2n e minus n into 2n square. Let me check once again. Maybe some mistake is there. Let me check. So nx, so we multiply nx is, so n into e to power nx square we have taken. So it is, sorry, what will be happen here? We have taken nx common, so it will be only one n here. When we are taking one n here, it will be n here, and it will be under root 2n. Okay, so it will be under root 2n. So this is equal to this. So what you got? You got 1 under root n by 2, and this will be e to the power minus 1 by 2. Okay. So what is this? Mn is equal to under root n by 2 e to the power 1 minus 4 all n belongs to n. But this part goes to 0 because n is here. When n tending to infinity, this will go to infinity. Okay. So this implies Mn does not tend to 0 as n tending to infinity. So what does it mean? It means Fn does not converge uniformly on. Okay. So today's lecture up to this. Okay. In this lecture we have find out an alternative way to check uniform convergence provided the function converge pointwise. Okay. So today's lecture up to this. You can comment anything on my YouTube channel related to this class. Okay. So kindly like, comment, share, subscribe my YouTube channel. Thank you very much for today's session. Thank you very much.